So we continue our discussion. In this section, we are going to have a look of the systems built by using the superchip from Nvidia and the MI300 APU from AMD. So in the previous part, we have discussed in detail the technical evolutions of the superchip from Nvidia. I mean the super Grace Hopper or the Grace Blackwell superchip, and also the APU, the MI300A from AMD. And then we compare these two chips to understand their technical evolution. Afterwards, we discussed the nodes, the gut socket nodes that could be found from the marketplace, which uses the super chips or the MI300 APUs. So, but you know, the industry is always aiming at big and huge systems. Here, what we have here, what you can see on the screen is the HPC system, the HPC and AI system built by Eviden for Hewlett Supercomputing Center. Hewlett Supercomputing Center means Hewlett Supercomputing Center, and which is a very famous supercomputing center from Germany. And this system was, it is #1 in Europe that has broken the 1 exaflops barrier. It's the first one to break this barrier in Europe, and it is actually right now is #1 in Europe. In Europe, it's #1 in Europe. Is on top 500 list. Top 100, and it is #4 worldwide. So this is the system. It's a real system that has been delivered. The benchmark has been done. It breaks the 1 exaflops barrier in Europe. And it is #1 in Europe. It's #4 worldwide. This is the system. It has been built and delivered by Eviden. Eviden is the French and Europe HPC wonder, HPC and AI wonder. Okay, we can have a look of this physical view of this compute node. Actually, it's a compute blade. And on this compute blade, what you can say is that you have 1, 2, 3, you have 4 super chips. Okay, these 4 super chips make a gut socket node. And this blade, the whole blade, is a node. And this is the logical architecture of this node. Let's have a look of this node 0. This node 0, which is a gut socket node, and it's a cache coherent non-uniform memory access node, the so-called CC-NUMA node. You have gut sockets, so you have socket 0, 1, 2, and 3. Totally, you have gut sockets, and each socket you have a Grace Hopper superchip. This is the node. This is just one node. Okay, and then the 4 GPUs in this node are interconnected each other by using the NVLink C2C, the chip-to-chip NVLink. Okay, it's a kind of auto interconnections between the 4 GPUs. Okay, and besides these 4 GPUs, the 4 CPUs are also connect each other using some kind of auto interconnection. And the interconnection is this one, is the Grace-to-Grace C-Link, which is the green one. The color is not so easy to to distinguish, but here this one and this one, which is the grid C-link. Okay, grid C-link is between two CPUs. Okay, the four CPUs are interconnected to each other the same way as the four GPUs. Okay, and then you have four InfiniBand adapters: InfiniBand adapter 0, InfiniBand adapter 1, InfiniBand adapter 2, and 3. These four InfiniBand adapters are connected to the corresponding sockets. So InfiniBand adapter 0 is connected to socket 0. InfiniBand adapter 1 is to socket 1, etc., etc. This is the logical architecture of the compute node. Okay. Basically, each from Nvidia, you have four superchips which are integrated each other like this, like our node, integrated together to make up a logical node like our node 0. This node is called CG4. Means that you have four. You have four. Means you have four sockets. So a GAT socket system made of four superchips is called a CG4. And CG4, the code for this blade is CG4. For this node 0 is CG4. It's just one node. It's a logical node, and it's kind of a CC Newman node. CC Newman node. Okay, that's okay. And we need to have a look at these four GPUs. The four GPUs are interconnect each other by using the kind of auto interconnections. And these four Hopper GPUs, you put them together. You put them together, you make an NVLink domain. It's called an NVLink domain. So the GPUs belonging to a single node, they are interconnected to each other by using NVLink. It's called NVLink domain. Because you have four GPUs, so this is an NVL4 domain. So NVLink domain with four GPUs, NVL4. Okay, here it is, NVL4. The system for this customer, each node, you have an NVLink 4 domain, NVL4 domain. Okay. Afterwards, we need to connect multiple nodes together to make the system. And here is what has been done. Basically, Evan has proposed to the customer the InfiniBand as the interconnection network to connect all the computing nodes. So each node, you have four InfiniBand adapters. These four InfiniBand adapters are all connected to the InfiniBand network, and that makes the final system. There is a name for this system. This system is called, the name of this system is called Jupyter. Jupyter Booster. Jupyter Booster. This is the name of the system. And it's made up of the quad socket systems with superchips, the Grace Hopper superchips. This is the system. Okay. Actually, the programming model for this system, is still MPI plus NCCL. MPI plus NCCL is still the programming model for this system. So this is the same as before. This is the same programming model. for GPU computing systems with SXM and OAM modules. With all this evolution of the superchip and the APU, but the programming model side, the programming model is still the same. There is no evolution from this side. So you still have to use this MPI plus NCCL to program for these kind of systems built by using the superchip and the APU from AMD. Okay, so okay, now maybe it's a good idea to have a look of this programming model for the GPU computing systems with SXM and OM modules. Okay, basically what you have here is that you have two nodes. Right hand side, you have this compute node, which is made up of this CPU. The CPU is x86, and you have multiple GPUs connected to the CPU. And then you have these GPUs also interconnect each other by using the NVLink. Okay? Okay. Because you have the NVLink, the communication between the GPUs connected to the same host. You have N GPUs connected to the same host. The communication between the N GPUs, basically, what you can do is that you can do peer-to-peer memory access, which is kind of communication. And between these GPUs, you also can do NVLink. You also can do NCCL communication. The traffic will be going through this NVLink. And the NVLink could be simple as some connections between the GPUs. I have just shown you in the previous slide that you have 4 GPUs interconnect each other by using the NVLink, C2C NVLinks. And it's a kind of auto interconnection, and you have this kind of NVLink network. And it could also be NVLink network with links plus switches. If you have more than 4 GPUs, pretty much you will need switches. So the NVLink network could be only links or links plus switches. But anyway, the NCCL communication between the GPUs will be going through the NVLink network. Okay, now here comes the concept of NVLink domain. If you look at these N GPUs connected to the same host, they are all interconnected by the same NVLink network. Because they are connected to the same NVLink network, we are saying that these GPUs are belonging to the same NVLink domain. And because you have N NVLinks, so we are going to say that you have an NVLink domain with N GPUs, NVLink N. If you have 4 GPUs, we are going to say that you have an NVL4. That means an NVLink domain of 4 GPUs, or we call it NVLink 8. If you have 8 GPUs, that means you have an NVLink domain with 8 GPUs. So here comes the concept of the NVLink domain. And peer-to-peer memory access is always within an NVLink domain. It cannot go across NVLink domains. So it can only be within a domain. Different from peer-to-peer memory access, the NCCL communication, at the first case, it can be within an NVLink domain. Here, if you have 8 GPUs, you have an NVL8 NVLink domain, and the NCCL communication could be done for all the GPUs belonging to this NVLink domain. So you can have this kind of NCCL communication. But different than this peer-to-peer memory access, the NCCL communication could go across nodes. Okay. Now here, left-hand side, we have another node which has exactly the same architecture as the right-hand side node. Okay, so you have x86 as the CPU. You have NVL 4 or NVL 8 domains. Okay, so you have another NVLink domain. Up to now, an NVLink domain can only be with only one node. That means the NVLink domain cannot be crossing different nodes. So an NVLink domain can only be attached to only one host. Up to now, this is true. So here you have two NVLink domains belonging to two different nodes. As I said, different than this peer-to-peer memory access, which can only happen within an NVLink domain, these NICO communications can go across nodes. But to go across nodes, you have to rely on another network, which is different than the NVLink network, because the NVLink network is separated for the two nodes. Okay. It could be some other technology. For example, it could be the Ethernet network, but the mainstream solution from the marketplace is the InfiniBand network. We use InfiniBand network as an example. So the NVLink traffic could go through the InfiniBand network, and the GPUs belonging to two different NVLink domains. That also means the GPUs belonging to two different nodes, they can communicate each other using this NICO communication library, but the communication has to go off this NVLink network and go through this InfiniBand network. Another point is that for this NICO traffic here, the traffic are in rails. Okay, so you have red, green, yellow. You have the same quantity of rails as the number of nodes connected to a single host. So the traffic could be separated into rails. Okay, that's for the NICO communication. At the same time, because you are using MPI plus NICO as the programming model, so at the same time, you also have this kind of MPI traffic goes across these two nodes. So MPI traffic will be for CPU to communicate each other. That means for the host to communicate each other. So the message will be from the CPU, from the host, and then to the InfiniBand network, and goes to the other side, to the other node, and goes to the memory of the other node. So here we have two nodes. You can have the communication between these two nodes. Different than the NICO communication, the MPI traffic, they don't have this kind of concept of real communication. That means the MPI traffic cannot be separated into different rails. There is no concept of real communication in rails. So that leaves a task for the system vendor to well balance the two different kind of traffic going through this InfiniBand network. We have this NICO communication traffic could be separated. The traffic itself could be separated into different rails. On the other side, the MPI traffic, this is the NICO traffic. The MPI traffic, there's no concept of communication in rails. Then for the system vendor, they have the choice to balance the needs of the NICO communication in rails and the MPI communication, MPI traffic without the concept of communication in rails. You have to, the system vendor have to design the network, the InfiniBand network, the interconnection between the nodes, this network, according to the nodes, and according to your focus, whether you are focusing on NICO communication or whether you are focusing on MPI communication, and then you need to balance the choice of the topology and for this interconnection network. Okay, that's the MPI plus NICO communication programming model for GPU computing systems with SXM and OM modules. Okay. Now we come back to our GPU computing systems with the super chip from Nvidia. For this NVL4 domain, you have the peer-to-peer. You can have this peer-to-peer memory access between the GPUs. And this peer-to-peer memory access cannot go across the NVLink domains. So it has to, that means the Hopper GPUs from this NVLink domain cannot access the memory from another node by using this peer-to-peer memory access. Peer-to-peer memory access is always within an NVLink domain. Okay, and then we have this NICO communication. The NICO communication within an NVLink domain, it goes through this NVLink network. Here we have between these 4 Hopper GPUs, we have auto interconnections of the NVLink C2C links. So that makes an NVLink domain. So the NICO communication can go through these NVLink C2C links, and the communication can happen within this NVLink domain. But the same as we have just mentioned, this NICO communication can go across nodes, means the Hopper GPUs from node 0, let's see Hopper GPU 0 from node 0, can communicate with Hopper GPU, here it is, Hopper GPU 0 from node 1. But again, the NICO traffic has to go through this network, this interconnection network that interconnects all the computing nodes. And for this particular system that has been delivered to Hewlett Supercomputing Center by Nvidia, by Aviden, which is right now #1 in Europe. The network has been delivered is the InfiniBand network, and the same as we have just mentioned, the NICO traffic are in reals. That means InfiniBand interface 0 only communicate with InfiniBand interface 0 from another node, and InfiniBand interface 0. Okay, so InfiniBand, there is the NICO traffic, the red one, which are going to be comes out from the InfiniBand port 0 and goes into the port 0 of another node. So this is the concept of the NICO communication in real. So this is the red real. Okay, so the NICO communication, as we have mentioned earlier, the traffic could be put on different reals. This is the nature of the NICO communication. But besides the communication between the GPUs, there are also the traffic between the CPUs that belongs to different nodes. So CPU 1 from node 0 need to communicate with other nodes, other CPUs from other nodes. For example, this you have another Grace CPU 1, so Grace 1, sorry for the color. This is Grace 1 CPU, and the Grace 1 CPU from node 0, it needs to communicate from Grace 1 CPU from node 1, and it also needs to communicate with the other CPUs from the same node 1. So it could happen. It could happen that Grace need to communicate with all the CPUs from another node. This is the nature of the MPI communication. There is no concept of communication in reals. And we could have the case that each CPU need to communicate with all the other CPUs. This could happen with the MPI communication. That depends on the nature of the computation, but this is something that could happen. Different from this one, the NICU communication are always in reals. Okay, so that means for this system that has been delivered to Hewlett Supercomputing Center, everyone has to conceptually choose the right topology to make the interconnection network low cost and with relatively good performance. This is the design target of the system. Okay, but back to the point is that for this kind of system built by using the Grace Hopper or Grace Blackwell super chips from Nvidia, we are still using the same programming model as the previous generation of GPU computing systems with SSM and OM modules. The programming model is MPI plus NCCL. Okay. And you also can use this peer-to-peer memory access to help with the communication, but this peer-to-peer memory access can only happen within an NVLink domain. So this is the programming model for the systems built by using the NVLink superchip. And that's pretty much the same story for MI300 APU. Okay. If you look at this picture, you have basically a blade from Cray. You have two nodes on one blade. Left-hand side, you have actually underneath this motherboard, this green motherboard. Underneath this one, you have a socket with APU MI300A. You have the first one. You have the second one here underneath this cold plate, and then you have another one underneath this cold plate, and another one underneath this motherboard, the green one. Okay, you have 4 MPI APUs which make up this gut socket system, and you also have 4 InfiniBand. You have also 4 slingshot adapters. Basically, each green motherboard, you have 2 adapters. One is connected to this APU underneath, the other one is connected to another APU, the neighbor one. The same story will happen for this green motherboard, which is slingshot adapter. It has 2 interfaces on this adapter. One is connected to APU in socket 1. The other one is connected to the APU, which is socket 2. So this one is connected also to this APU. That makes 1 PCI interface per APU. Now, this is the photo of this compute node. if we look at this logical architecture, is more clear. You have 4 APUs, 4 sockets, so guard socket system with 4 CPUs, 4 APUs. But each APU is going to be connected to a different PCIe adapter, because this system is using the slingshot interconnection network from Cray. So here, basically, we have seen a motherboard in color green. This is a motherboard. Okay, for this motherboard, on this motherboard, you have 2 PCIe adapters, which equals this green one. Okay, so you have 2 green motherboards that give you 4 PCIe interfaces to connect to this system. And finally, you are going to make up a node of 4 MPI+300 APUs, and you have a node, which is node 0. And then you need to have multiple nodes to connect these multiple nodes to make a big system. And for this particular node, it always goes with HPE Cray slingshot. This is HPE Cray EX255A system. A means APU. So it always goes with slingshot. So the network for the system to interconnect the multiple nodes, the network is the slingshot. Okay, but the same as we have just discussed here, the NICO traffic, no, we don't have NICO traffic. The fact is that between these 4 APUs and on top of each APU, I mean this chip, on this chip you have multiple XCDs. XCD is an accelerator compute die. We can safely say that each XCD is a GPU. And on this chip, you have multiple GPUs. You have another multiple GPUs on another chip. So you have multiple GPUs for each socket. And the sockets, the APUs, also means the GPUs are interconnecting each other by using the Infinity Fabric. The red one is the Infinity Fabric. This is the link between the 4 sockets, between the 4 APUs, between the GPUs on the chip on the MPI+300A chip, the multiple GPUs on this chip. Okay, so you have Infinity Fabric between these GPUs. Then the communication between the GPUs here is that first you can do peer-to-peer memory access. This one, the green one, you can do peer-to-peer memory access. And the same as for Superchip. The peer-to-peer memory access cannot go beyond an domain, an Infinity Fabric domain. Okay? Now, we need to have a look at this Infinity Fabric domain, because we have just mentioned that the 4 GPUs interconnect each other by using NVLink. That makes up NVLink 4 domain. So we use the same concept because the GPUs belonging to the 4 sockets, they are interconnect each other by using this Infinity Fabric link. So we are saying that this domain is something similar to the NVLink domain, but here is Infinity Fabric domain because you have 4 sockets, so it's Infinity Fabric 4. Infinity Fabric domains, so IF4 domains. Within this domain, as I have said, you can do peer-to-peer memory access, And then you can run this RICO communication library. You use RICO to make the GPUs communicate each other, as it has been shown here. Okay. But the same as for NVLink, the same for Superchip. The RICO communication can go across nodes. That means the XCDs, the GPUs on this MS300A APU, they can communicate with the GPUs on this MS300 APU. If they have the same socket number, if this socket 0, this should be also socket 0. That means the traffic, the NICO traffic, is for here is RICO traffic. For AMD is RICO traffic. RICO means ROCm Collective Communication Library. That's the communication between the GPUs. The RICO traffic between nodes are in reals. So that means GPUs from socket 0 will only communicate with GPUs coming from socket 0. So you have socket 0, you have socket 0, you have GPUs on each socket, and the GPUs will communicate each other by using this red rail. So the RICO communication, the RICO traffic are in reals. The traffic could be separated into 4 reals. So then this gives you the possibility to build up a network which has 4 reals. Okay, real network in reals. That's possible. But the fact is that the same as for NVLink Superchip, the MPI traffic between the CPUs, because on each socket, besides this XCD, you are going to have the CCD. CCD is something like the CPU. So you have 3 CCDs. Is similar to the fact that you have 3 CPUs on each socket. You have CPUs on each socket, and the communications between the CPUs within the socket and beyond this socket, the MPI, the CPUs are not the same as the GPUs. They are not communicating each other as the GPU has done in reals. The CPU communications are not in reals. There is no concept of communication in real. The communication cannot be separated into different reals. Okay. So that means for the system vendor, when they are going to deliver the system to the customer, they really have to balance the system design. NICO, if you focus more on NICO, you can propose to the customer a network with 4 reals. That's going to help to reduce the cost. But that's not something good for MPI traffic, because for MPI traffic, there is no conception of communication in reals. MPI traffic cannot be separated into different reals. Okay. So if you want to focus more on the MPI traffic, you have to balance your choice: real network or a network totally without the concept of reals. Or you can propose to the customer a network at the beginning with multiple reals, and then you build up your network and you build that another layer for your network for these rails to communicate each other. So for the traffic, for the MPI traffic to go across the rails. Okay, that's another topic we should have covered in section 4. But for this system, is conceptually is the same thing as for the systems built by using the superchip. The systems built by using the AMD APU follow the same logic as for superchip. And this architecture is not an imagined one. It's based on the real system. If you look at the 2025 June, you have this top 500 list, and the number 1 worldwide is the system for Lawrence Livermore National Labs, and this system has been built by using the MI300A APU and is number 1 worldwide in terms of its performance. Okay, and this architecture shows exactly the high-level architecture of this system, actually number 1 worldwide. Okay, but the fact is that even with all these technical evolutions from a superchip side and from APU side, the programming model has not been changed. MPI plus RICO for AMD is still the programming model for the systems with the superchip or with the APU. Okay, this programming model is the same as the programming model for the GPU computing systems with SXM and OEM modules. Okay, so that's the same thing. So the system, the superchip, the superchip has been evolved. The MI308 APU has been designed with a lot of technical evolutions. The same for superchip. It has been advanced so much with quite a lot of nice features. But from the programmer's point of view, the programming model for the systems built by using these two kinds of new chips, the Grasshopper or the Grace Blackwell superchip, or the MI300 APU, the programming models for the systems built by using these two kinds of chips. The programming model stays unmodified. It is still the same programming model as for the previous generation computing systems, GPU computing systems. Okay, so let's conclude this part. The key message is that MPI plus RICO or MPI plus NICO is still the programming model for the GPU computing systems with Nvidia superchip or with AMD APU. The programming model remains unchanged. And up to now, the peer-to-peer memory access is always within an NVLink domain or within an Infinity Fabric domain for AMD. The NICO communication goes through this NVLink network within an NVLink domain for node. This is the NICO part for this MPI plus NICO programming model, but this NICO communication can go across nodes. Okay, the same for the RICO communication library. The recall communication can go across the nodes, but this leaves the system under a technical choice, a topology choice for the interconnection network to interconnection network to interconnect all these computing nodes. So you have to balance the choice on focusing more on equal communication or more on the MPI communication. Okay, so up to now, this NVLink domain is within a node. The NVLink domain is not across nodes. We are going to say that for the new evolution is that the NVLink domain is going to be across multiple nodes. At the same time, we are going to find out that this peer-to-peer memory access is going to go across multiple nodes. That's for the next section. Next section, we are going to have a look of the most recent evolution from Nvidia side, which is the NVL72 domain, NVL72 system, how to program this kind of system. So stay tuned. We are going to see you very soon. Okay.